for having heeded my emails, even as he was in Israel. He had yet to come to the US, but he made the commitment to come here. And I'm so tickled pink. And I'm also very grateful to his host family. Some of you may know them. Norris and Doris, Dr. Keynan.
Thank you. So first of all, I'm really happy I came. I tried to dodge it, I'll be honest. When Johnny wrote me and asked me to come a few months back, I said, well, I just relocated to America with my family, it's too soon. And he answered, it's 2 months after you come, you'll be fine. And well, I am fine and I'm having a great time here. I hope the folks at Stanford won't hear that I said that they're from plastic. So I need your confidence. Yeah. Okay. So I did my PhD in Tel Aviv University in an institute called Sagol Brain Institute. It's a shared institute for the Tel Aviv University and the Tel Aviv Medical Hospital, the big hospital of the Tel Aviv area. Serves about 3 million people. There I was supervised by Professor Talma Handler, and today I'm doing my postdoctoral work at Stanford Medical School, supervised by Professor Amit Atkin. I'm mentioning both of them because a lot of the research that I'm going to show you was initiated and thought about by these two brilliant investigators that I hope one day I could be even a little bit similar to them. Okay. So my research so far focused generally on the connection between the human mind and the human brain, and how by understanding the brain can we help the mind. In specific, I focused mostly on stress. What does stress does to the brain, and what does the brain does to stress? So as we go along, I'll try to clarify what that means, what the brain does to stress. But before we dive in, sorry, I'll get used to that. Okay, before we dive in, let's appreciate together for a moment the amazing complexity of the human mind and the human brain. So this is a metaphor that I like from a writer named Damasio, comparing the human mind to a tree. At the top of the tree, the leaves, if the tip of the iceberg, if you will, are feelings, are sensations. I feel something in my hand, I feel angry, I feel sad, and together with them, but a bit underneath is the emotions. Humans have complex emotions. We can have multiple emotions at the same time, and most of our emotions we're not even aware that we have them when we have them. Underneath that treetop are drives and motivations. What motivates us to do what we do, which again, I guess, please come in, sit down. Excuse yourself. Which again, I guess, most of us are not fully aware to what motivates us and drives us to do what we do. We all try to avoid pain and seek pleasure like any other animal. And at the bottom of the tree, we have all of our body, our immune response, basic reflexes, and metabolic action. Now, the amazing thing is that it is all, sorry, I'm not used to this clicker yet. It is all in our brain. Now, what is our brain? Is it a computer algorithm? Is it a biological process? Is it a psychological process? Well, apparently it is a little bit of all of these things. So our brain has billions of cells, what we call neurons in the brain, and each cell in the brain makes connections with approximately 10,000 other cells, adding up to roughly 10 by the power of 16 overall connections. Now, when I was making this presentation, I tried to explain myself to comprehend what is this number, 10 by the power of 16 connections. So it is 100,000 times a trillion. Okay, 100,000 times trillions. Trillion, that's 1,000 billion. Try to imagine that number. I think if you take a look at the stars at night, I'm not sure you're going to find so many stars. So perhaps when we say that each person is a world of its own, perhaps we should be saying each person is a universe of its own. And that's just to give you how hard it is to investigate the brain and to understand the brain that has as much as connection as we have stars at night. Some amazing numbers. Now I have 2 kids, so I like to look up things about how their brain is developing. Babies up to the age of 1 form approximately 100,000 new cells per minute. So that means that when my son is feeling something for the first time, his brain is actually making the cells that can sense what he's feeling. So the feeling is forming while you are experiencing it. With adults, approximately 10,000 per day. But still, we're making new cells. Cells are dying. We're making new connections. Old connections are diminishing. Our brain is constantly forming and changing. And the big question is, can we harness this plasticity, this amazing plasticity of our brain to heal ourselves? And okay, so another thing we'll talk about is how can we investigate the brain? What are the tools that we use to investigate the brain? So with humans, we will use non-invasive imaging. And the most famous one and the one that gives us the most, let's say, comprehensive information is MRI, magnetic resonance imaging. MRI gives us both structural mapping of the brain, so how the brain looks, what is the size of different regions in the brain, what areas are physically connected to each other. And we also get what we call fMRI, functional MRI. We can get a picture of how the brain is working, of what areas work while we experience. So I'll show you a movie, I can let you listen to things, make you feel things, and I can have this yellow dots there that will tell me this area, the activity in this area is now rising, or blue dots tell me the activity in this area is now diminishing. So I can take a look of how the brain is mapped, physically connected, and what areas are working and what areas are working as a network, or what areas are working as different networks. We also have cheaper and mobile imaging techniques, such as EEG. The problem with MRI is that it's very expensive, immobile. About 20% of the individuals cannot participate in MRI experiments, because if they have a metal in their body or anything else, we put them there only if we have a pressing medical issue. But the problem, so EEG doesn't give us these beautiful pictures that we can look at and make sense of. EEG gives us electrical activity measured from the skull. It's still brain activity, but as you can see, it gives us these frequencies and power, and it's a bit harder to understand than MRI, and I'll try to, once we go on, I'll try to explain to you a bit how we can try to make more sense of the EEG. So traditional EEG, I can tell you now you are very aroused because I will see a rise in certain frequencies, or now you're very relaxed because I will see a rise in different frequencies. But I can't really tell you, now your cognitive system is very active or your emotional system is very active like I can do with MRI. Okay. The neurons that I told you about form networks that organize our experience. So we have a network of perception and sensing. Once we feel something or hear or see, it is processed there. It's processed hierarchically mostly. So first we process lines, and then we see that it's an X, and then we see the meaning of the X, and it all happens in milliseconds once we see it. We have this limbic system, which is my main interest, and how it interacts with the rest of the brain. That's where most of our emotions are elicited, and it also the system that's in charge of keeping us vigilant and going downstream effects of hormones and so on. Sorry. Okay. And the most unique about human, we have this very big prefrontal cortex that is in charge of cognitive control and emotion regulation. For example, if I feel very angry and want to do something, this is the system that's in charge of telling me move on. So this is what differentiates us most from other animals. When we ate the forbidden fruit, if you will, God punished us by growing this prefrontal cortex, and since then we are aware of ourselves. We can think about what we are feeling. We can think about other people feel, what they feel about me. We can have guilty conscience, and I should have done that, and I should have done this. And we have a lot of problems because all of that self-reflection. But it's also very important to us. It's what makes us human, and we need these two guys to talk very well to each other. Okay. What happens to the brain under stress? So let's, for the sake of this discussion, define stress as any kind of emotional distress that is elicited in reaction either to physiological stimuli or psychological stimuli. So, stress up to a point is actually adaptive. In here you can see a scale of performance, and in here you can see stress and how the performance changed with regard to how stress changes. And so, some stress we needed actually to perform. For example, I was a bit stressed of having to do all of these talks. I always want to make a good impression. But it made me sit down in home and prepare and make this presentation. If I was to become too stressed, I would delete this slide again and do it again and again. And when I would come here, I'd have my mouth run dry, and I would be sweaty, and I couldn't do it very well. And the interesting thing about and now in the extreme level of stress is what we call traumatic stress. Now, traumatic stress, we mostly refer to it as either bodily injury of myself or seeing someone else being injured. But it can be other things. Traumatic stress is pretty subjective, what is traumatic and non-traumatic. And what's incredibly interesting about humans is that our stress curve is very different. What could be traumatic stress for myself could be actually the optimal level of stress for another individual. And that variability between human beings is something that we're trying to investigate, trying to see if we can predict the stress curve of different people. Okay, so under stress, the first system that comes into play is this limbic system. It's like the alarm bell of the brain. Now, an alarm bell is a very important thing because it tells us, hey, there's something here that we need to notice. But try to imagine what happens when the alarm bell goes out of control. When I was in a bachelor degree, I worked security in the Bank of Israel. It's like the Israeli Federal Reserve. And once you finish your training, you're very happy with yourself, and you come to the control room all feeling macho, and they do you this final test which everybody fails. They sit you in the control room, and they sound off all of the alarms at once, and they're pressuring you, okay, what do you do, what do you do? And I'm like, well, I'm calling this team, and I'm calling this team, and I'm opening the army, and I'm running to the security room. And every time they will, hold on, Rambo. The first thing you do is you turn off the alarms. Okay? If you try to do all of these things and the alarm bell is in your head, you're not going to do nothing. I'll say normal, or normal is not the good word, maybe the healthy situation. What will happen next is that this control room here will get the information that there is some kind of alarm, not yet knowing it could be a good alarm. Maybe it's ice cream, not someone want to kill me. But it will get the message that there's something important going on, and it will tell to the limbic system, thank you. I've realized that there's something going on. Let me please talk to other parts of the brain and try and understand, what do we do now? Do we need to plan any kind of motor action? Do we need to freeze? Do we need to fight? And after the stress is over, and that's perhaps even more important than what we do during the stress. After the stress is over, this system right here, if it managed to make the alarm bell go quiet, then it can say, okay, the threat is over. Let's now see that on myself I'm okay, on my friends okay, and if something terrible happened, then what can I do about it? And we start reappraising. Well, I can get over this. Someone will come to my help. I will grow and get over this. But if we fail in this thing and the alarm bell is still kicking all the time, then all of these recovery processes can't really take place. Okay. So, unsuccessful recovery can lead to chronic stress, a chronic feeling of stress and vigilance and hypervigilance, which in turn can cause mental and physiological illness. Now this is what I want you to see next, is an amazing figure estimating the cost spent to treat different physical and mental conditions both worldwide and in the US. So at the top of the line you see addiction, anxiety, obesity, chronic pain, migraine, depressive disorders, sleep disorders, which are all of them are stress related. So in modern society, it's not only traumatic stress that we are concerned about, it's even any kind of stress. It's work burnout, it's burnout from studies, any type of stress, even if it's not the traumatic stress, but for a long time, if you don't deal with it appropriately, it can lead to any kind of mental or physical illness. So, the most, I'd say, famous or infamous type of stress psychopathology is post-traumatic stress disorder. And this mostly happens after traumatic stress, not chronic mild stress. And it's characterized by intrusive thoughts and re-experiencing, remembering things from the traumatic event, and having trouble getting these out of my way so I can concentrate on other things, and sometimes even re-experiencing of the bodily sensations that I had during the traumatic event. Avoidance from anything that would remind me the traumatic event. I had patients telling me, you know, I drive my car 40 minutes longer just so I won't have to go through that damn junction when I had my car accident. That's the normal case. It can get much worse to people that have agoraphobia. They close themselves in their own home just so they won't have to see anything that might remind them of the traumatic event. Hypervigilance, as I said, the alarm is always going on, even if it's not a real threat, you always, well, then that's anxiety. It's not fear from a real thing, but it's anxiety, always feeling that there's a threat above you. And of course, we're having all of these things. We also see negative alternations in mood and cognition. Could be depression, could be deterioration in our ability to concentrate and function in work. Now at the brain level, many things are going on. Okay, we have problems with memory areas, with cognitive functioning areas, but I will concentrate on that example I gave you about the alarm bell. This area here is the blue here is called the amygdala, and with PTSD patients we see an elevated amygdala activity, so alarm bell always working, and perhaps equally important, or even more important, we see decreased connectivity with the prefrontal cortex, with the control room of the brain. So now the alarm bells are going off, the control room is not there to tell the alarm bell you can stop working. It's not something very threatening. Now, in our research we did with Israeli soldiers during so it accidentally was during the Second Lebanon War, we actually found that this hyperactivity of the amygdala might not, or perhaps not only be a result of trauma, but can actually be a predisposing vulnerability factor. So we had the soldiers, they did fMRI before they went to war, and after. And what we found is that soldiers that had hyperactivity of the amygdala before battle were more prone to PTSD after trauma. So, how can this help us, knowing all of these things about the brain? So, I'll start by one way of direction, which was mostly in Tel Aviv, which is to develop new treatments that will have specific targets in the brain. So, we know that hyperactive amygdala indicates stress vulnerability. Perhaps we can learn to downregulate our own amygdala activity. Now, how do we do that? We do that with a thing called neurofeedback. What is neurofeedback? This is the definition here, but I'll explain it like this. So, let's say I want to learn to ride a bike. I do it by trial and error. Do something, I fall, then I don't do it again, I'm going to do something else until I don't fall. But the way I can learn with trial and error is that I have natural feedback. I see where I'm going, and I have proprioception. I can feel if I'm stable or not. So this constant natural feedback helps me learn what I need to do to ride the bike properly. In the brain, we got nothing. Nobody here knows, if I ask you, how much is your amygdala active right now? Is it more than before? Is it less than before? Nobody knows, because we don't have any natural feedback from our brain. So what we need is some kind of artificial feedback that, like the bike, will tell me, well, now your amygdala is downregulating, keep doing what you're doing. That's what we call neurofeedback. We measure brain activity continuously, and we give the individual feedback of his activities. And we try to do it in sophisticated ways. Let me show you a video. So, what you saw there, I'll just let it run a little bit more. Sorry. Okay, sorry for that. Okay, what you're seeing here is the subject wearing EEG. The EEG continuously measures amygdala activity. EEG is not meant for that. If I'll have time, I'll explain how we do it with EEG. And at first, we ask the participant just to watch this situation. So I'll try to pause it again so I can explain. If I can find the pause button. Yeah, okay. So, what you saw is on the screen, the subject sees a simulation of a very agitated hospital waiting room. You saw an actual recording from the waiting room in Israel, all these shouts and complaints, and you see people congregating near the reception. And at first, 1 minute, you're just watching it without doing anything. Then, we ask you to focus on the situation and try to do some kind of mental exercise that will cause people to lower their voices and sit down in their place. And what you see here is this red line that represents the activity of the amygdala. Once the computer senses that the activity of the amygdala is starting to downregulate, it makes people sit down and lower their voices. And we do it again and again and again until it becomes like second nature. And eventually we try to do it without feedback. Just downregulate the activity, and I watch my computer to see if you succeed. Okay, so one question I get a lot is, what do people do? What do they do to downregulate the amygdala activity? Now, the beauty I think about neurofeedback is that each person has to find his or her own way. We don't tell the subjects what to do. They have at least 4 sessions that they try different things, like I concentrate on a specific part of the simulation, I concentrate on all of the simulation, a lot of games with the amount of focus and engagement that you need with the situation until you find the way that for you, the amygdala is down-regulating the best. Okay, so I have until, Jami?
You have another 10 minutes for quick Q&A.
Okay, so on this one I'll have to skip forward a bit fast. I told you EEG. Anyone that knows about EEG, if you tell them you met a guy that measures amygdala with EEG, he will tell you, well, that guy doesn't know what he's talking about. So what we did here is a study that we did machine learning on EEG acquired simultaneously with fMRI. And we applied machine learning on this, and we developed a model that can predict amygdala activity using only EEG. I won't get into the details, but the point is that we took the EEG with a cheaper and mobile device that you can use at your own home, and took some of the accuracy of MRI to bring with it, and we were able to do this study with EEG. We did a study with 180 newly recruited Israeli soldiers, this time not traumatic stress, but in Israel, military service is mandatory. Once you finish high school at 18, you go to the military for 3 years. So we did this study in the first few weeks of basic military training. That's a very stressful period. The first few weeks you're away from home and you're training in the military. And the soldiers that you see in the pictures, they did 6 meetings of this neurofeedback trainings during basic training within 1 month. And what we saw is that first of all, they learned and gradually improved in their ability to downregulate amygdala. You see here, each dot is a session, and this axis here tells you how were they able to downregulate the amygdala, and we see that it gradually, session after session, goes down. So we're very happy about it. We saw that our control group, which did a training not aimed for the amygdala, did not learn to regulate the amygdala, so it's not just placebo. So we're happy, we're saying, okay, we trained our brain. And even more importantly than that, in following fMRI, we saw that the soldiers that trained to downregulate their amygdala had a higher connection between the amygdala and the prefrontal cortex. Okay, meaning the alarm bell and the control room are now better speaking to each other, which perhaps is the main thing that we wanted to achieve. And of course, with the indication that we have, remember, it's not traumatic stress, it's like preclinical stress. We saw that they were less vulnerable to the detrimental effects of this stress during basic military training. Now, with participants that already have PTSD, what we thought about doing is not just letting them train with this natural context of the neutral, context of the waiting room, but after they do a few sessions with the waiting room, they go on and learn to downregulate amygdala activity while they listen to their own traumatic narrative. Okay, at the start of the treatment, they record, they tell their traumatic story to another person. This person creates a script where he tells the traumatic story. And now we're saying to someone, okay, you learn to downregulate the amygdala in a different context. Now we're going to play you the audio playback of your own traumatic story, and you learn to downregulate the amygdala while you're doing it. So in a way, try to recode the traumatic memory. Now, we didn't invent neurofeedback. We didn't invent prolonged exposure. That's a very famous treatment for post-traumatic stress. We did manage to do neurofeedback for amygdala, which was pretty new. And this concept of trying to integrate between insights from psychotherapy and from neuroscience to target specific brain activity in a specific context to make this context less traumatic. And in the study we just finished, we actually saw that indeed, when you do these two together, it's better than doing just neurofeedback. We're also testing it. We still have to prove that it is better than just doing prolonged exposure and better than placebo. But that's a novel direction that we're currently investigating. Okay, so just a few more slides. I told you about Tel Aviv mostly. I'll tell you about Stanford, where I just started. So one of the challenges we currently have in psychiatry, not only in stress, but in depression also, and other mental illnesses, is that we have a lot of treatment: psychotherapy, neurofeedback, drug therapy, TMS, which is a method to externally stimulate brain activity. But together they have unsatisfactory efficacy, each of their own. And more importantly, it can take up to a year for someone to find the treatment that actually works for her. And most people just drop out. They give up in this year because, especially if they take medication or go to psychotherapy, with medication they have a lot of side effects, not getting the real effect, but just the side effects. And with psychotherapy, you invest a lot of time and a lot of money, and you're not seeing results, and people just get tired of it, and they stop switching between treatments and just give up. So, and we don't currently have no way of guessing. What we are doing is guessing, trial and error, what treatment will fit what person. So my current mentor at Stanford says, well, perhaps the treatments are working just fine. Perhaps the problem is in diagnosis. Perhaps the treatments are working for the ones that it's working for. And what we need to find is how to fit the right treatment to the right person. And I'll show you two examples of how we do it. This is one study that was published in Science Translational Medicine. So we knew two things. We knew that memory functions have something to do with the way that people stick to treatment. And we also know that this area here is very important to cognitive functions, and it's called the ventral attention network, for attention. Now, what we found in this study is that you see here 4 groups. We have a group that's not abnormal, that's totally healthy both, and all of these people have PTSD. So we have a group that's healthy both in the ventral attention network, and both memory functions are working fine. We have a group that has an abnormality only at one of them, and a group that has an abnormality both in the ventral attention network and in memory functions. This is the blue group you see here. This is before they went to treatment and after. So we found that if you have abnormality both in the ventral attention network and you have impaired memory functions, then you'll probably won't benefit from traditional therapies such as drug therapy or psychotherapy, and you need to do something else. Okay, so that's one lead that we can find. We can save all of this trouble to this person. Don't go to these treatments. You need something else. And we went a step forward. As I told you, MRI is very expensive. We can't have every PTSD patient do MRI. There's not enough MRIs for that. And here we did an analysis on resting state EEG. Now with EEG, if you remember, I showed you this picture of the stars. It's really hard to understand the information that EEG gives us, but it gives us information. So this time we again went to machine learning, and we asked the computer to give us 2 types of people according to resting state EEG data. Just classify them to type A and type B. But don't just classify to type A and type B arbitrarily. Try to find me a type of EEG that responds to this treatment and a type of EEG that will respond to different treatments. And what we found is that type A can respond to medication and psychotherapy, but type B responds best to TMS. This is, if neurofeedback you learn by yourself to regulate brain activity. In TMS, we externally upregulate with magnetic stimulation, not as scary as it sounds, you don't really feel anything. With magnetic stimulation, we make the prefrontal cortex work on upregulated activity. So this is a very important finding. I can't explain, a lot of people want an explanation of why this type A medication and why this type B You see a mess? Well, the brain might just be too sophisticated for us to understand. And science always says, understand, predict, control. That's the goal of science. But perhaps we can be satisfied with predicting and controlling and understanding later. This was the nice thing about this study. Very talented guy named Wei Yu. The nice thing about this study is we'll replicate in a lot of data sets. So in one data set, if you do machine learning, you will find something that might be accidental to this sample and not replicate to another sample. This was replicated a lot of time. It was just accepted to Nature Biotechnology. It was a very impactful paper. So this tells us we can probably use just this 5 minutes of resting state EEG and at least have some clue of whether this person should go to traditional treatments or some kind of other treatment. And now we're hoping to maybe have not just type A and type B, but also type C and D. And so we can be very specific. So this definitely psychotherapy. This is a combination of psychotherapy and medication. And to save all the trouble now, 5 minutes of resting state EEG is definitely something that every PTSD patient can do. It doesn't cost that much. Okay, so to summarize, first of all, examining the brain can allow us to relate our experience and even future feelings of ourselves to existing brain patterns. Finding something that relates the experience to a brain pattern makes it possible to develop new treatments to control this specific brain pattern. And by understanding our brain, we can start on personalizing psychiatric treatment, which is way, way behind all other medical treatments, which are now strong into this personalization. And that's it. If you have any questions, I'd like to take. Thank you.
In your study where you trained the amygdala, or
Yeah.
trained the people with the trained their amygdala, did you continue